All right. Hello, everyone. In this video, I'm going to walk you through the implementation of a for loop, a counter control loop in C#. But first, we'll just talk about what is required in order to implement a counter control loop. What are the required pieces? And then we'll go through again a solution to a problem as a means to introduce the for loop to you as a structure. So the objectives for the lesson are to explain the requirements for counter-controlled loops, and we will then describe the three parts of a for loop. So those requirements for counter-controlled loops, those basically get collected and then placed within the structure of a for loop. And then we'll, of course, like I mentioned, use a for loop in a solution to an actual problem. So without wasting any more time, let's get it. All right. So if you can see on my screen here, I'm just again using existing problems from the practice problems that are posted to your class. In this case, I'm looking in the Loop Problems 3 document, and we will just use this first question problem as the example that we can walk through to implement the for loop. To save us a little bit of time, I've already gone ahead and done the restatement and the modeling of the problem, but I'll just quickly walk through it with you here so you get a sense of where my head is at and how I created the restatement and the model, and then we can get to the planning piece and start talking about how to approach these problems that require looping solutions. So really quickly here, reading off the question to you, a bacteriologist determines that the approximate final population of bacteria in a culture after a time in days is given by the following formula. So we have a little bit of arithmetic to do, but again, nothing too crazy. That formula looks like it should be okay to implement. And we're told here where the initial population is the number that was present at the beginning, and then there's a special note that the initial population doesn't change. I'll come back to why that's important to note in a moment. And then we let the user input, so here's where things are coming into the program, an initial population, again, which is the amount of bacteria present, and a growth rate as a percentage. Okay, so those are the things that we're going to be asking for from the user. Okay, once you've got those input values, we're going to compute the number of bacteria in the culture for the first 10 days. Okay, so after day 1, we want to know what the population is. After day 2, we want to know what the population is, etc., etc. Okay, and it says do this in a loop. If we couldn't have already guessed that a loop is probably the best structure, but it's not obvious, and again, I'll mention why in a moment. We want to be able to see all the results in a table. Okay, so we're not just going to spit out the numbers. We want to have a table with headers and nice columnar formatted output so that it looks nice and is easy to read. Okay, and then finally here it says as a note, the number E is the mathematical constant. That's the base of the natural log, and we give it an approximate value. Okay, and then the final piece, which is important for us, is that it is also available as a property on the C# math class or the math library. So we can just get access to it there. When it comes to implementing our solution in C#, we don't necessarily need to declare a constant for that. We can just use it in the library. Okay, but again, I want to distinguish clearly the difference between planning and code implementation, so we'll still use it as a constant in our plan on its own. So if you read through this and take some time to really tease out the noise, this is the first problem statement that I've approached with you through these videos, which is a bit more complex. Okay, and there's more information here, some of it important, some of it not so important. For example, I don't really care that there's a bacteriologist and the approximate value is whatever. There are, I mean, that's irrelevant, but there are parts of this problem statement that we have that are very important. So in terms of understanding it, I've restated the problem in this way to really just cut away the noise and be left with the important piece. And that is to calculate the population of a bacteria culture given the initial population count and a growth rate. Okay? The population must be determined for 1 day through 10 days, and the results must be displayed in a table. Okay, so again, that is much shorter than what we see over here. And I've not brought over the formula and the requirements for the header values. Those can stay here. My restatement of the problem, again, is really just to show to myself and to others that I have a good understanding of what the problem is. Okay, the various minute details will come out later, but if I had to boil what we see here in the document down to, well, what is the core of this problem? That's what it is to me, right? We get an initial population, a growth rate, and we calculate final populations and display it to the user. All right, that's the problem. Oh, and by the way, we do that for a period of over 10 days. Okay, that's it. So I've cut away the noise. That's what I'm left with. The model, again, if you have access to diagramming software or something, you might want to go about creating a more elaborate model. But for now, this is enough to just get the point across. What we're going to do is ask the user for input, right? We need the initial population count. We need a growth rate. And then we're going to calculate and display the final population times 10 days, right? So over 10 times, we're going to calculate and display this population. That, to me, again, is a very short model of what the implementation of our solution could look like. Again, if you're more visual and you want to use visual tools to go through that process, please be my guest. All right, so now it comes to the planning piece. Now, it may not be obvious at once that this requires you to use a loop. Again, I've placed that in the problem statement itself. It says here, do this in a loop, so you can't get around that. But the crudest method for solving this problem would be to simply perform this calculation 10 times, right? So you would just to figure out a variable, let's call it final population, you'd assign it a value for time day 1 and assign it and then display it. And then you would just copy and paste that, 9 more times, changing the value for time from 1 to 2 to 3 to 4, etc. Okay. And, given that we're only asked to show 10 values, that might seem reasonable. It's not too bad. You copy paste times 10, you change 10 numbers, you're done. But if I came to you and said, okay, I want to know how that population is going to grow over 100 days, all of a sudden the prospect of copying and pasting and changing a number 100 times doesn't seem as inviting. So again, it's not always going to be obvious that a solution requires a loop. And in many cases, we're presented with problems like this one, where it would be possible to get away with a solution that doesn't use one. But I'm going to encourage you, where you can, to identify where looping would be useful and implement it. Again, the idea that in programming, the power of repetition is really the most powerful structure that we have is true. It can save a lot of time in terms of efficiency, planning, and maintenance of programs if you identify and use loops effectively. So let's just get to the planning stage here. And again, what I'm going to recommend is, in cases where you have a loop where you might repeat statements, the idea is kind of implicit in that whatever you're being asked to repeat, you're going to do it at least one time. So if you can, if loops are daunting or challenging for you, especially now as you're learning about them, if you can just forget about the looping part of it for a moment, just create a solution that is like the solutions we've created to this point, which is just sequenced from start to finish. So in this case, we know we're going to want to display the final population for at least day 1. So let's just first plan and implement a solution that just shows the final population after day 1. And after we're convinced and confident that our solution is good for working through the display for 1 day, then we can revisit the plan and then think about how we're going to modify it to repeat that statement, the additional 9 times, as it were in this case. We don't need to worry about the looping up front, right? We can get a large portion or part of the programming kind of out of the way and then just come back after and focus on the repetition piece. So running through the plan here, we know we've got some input that's identified. We also have some output, and we're also being told we've got a constant literal value here, at least one. There's another one that if you are careful, you could see it, but is not necessary at this point. So let's just go about declaring some variables that we're going to need. So we're going to need the initial population. And again, I'm going to assume that we can't have, fractions of bacteria. So I'm going to define that as an integer. we need to have a final population as per the formula that we're given. And again, I'm going to assume that we can't have partial bacteria, so we'll have an integer final population count. And then we're going to have a growth rate, which we're told is being entered as a percentage. So maybe the growth rate is 7.5%. So in that case, we're going to need this as a floating point value. So we can get the growth rate as float. Okay? And then finally, we're going to need our const E, and that's going to be as a float as well, and we'll initialize it to the value that's given. Oops, 71828. Awesome. I'll be a bit more specific here. Constant. Okay. All right. Fantastic. So we've declared our variables. Those are the things we need. We can then go ahead and we would want to display a program title. I'll let you know, when it comes to the implementation, we can get fancy, but let's just in the plan indicate that that's what we're going to do. And then we can get to prompting for our input. So let's do a prompt. We'll just say enter initial population. And we're going to store that in the initial population variable. Okay. And then we're going to also prompt for the growth rate. And I'll indicate here that that should be as a %. Okay. And then once we've got our inputs, then we can perform our calculation. So we will set the final population equal to, it says here, the initial population. Now this is important to note in the original problem statement. It says here the initial population does not change its value. Okay, and so what that means, going back here, is in this expression, in this calculation, it doesn't matter what day you're looking at. If you're looking at day 7, the final population on day 7 is going to be equal to whatever the initial population was at the beginning of the observation period, so day 1. Whatever the user entered, that's always going to be the value here. You're not going to modify and change that. It's not the day before. It's the initial population, and then we're going to multiply that by this value that has a variable for the time. So depending on the day, this is what will modify the final population. We're not changing the initial population variable. So the final population is equal to the initial population, and we're going to multiply that by our constant E to the power of, and in this case, it's the growth rate multiplied by time. Now, we don't have a time variable, but let's, like I said, just create a solution that works for day 1. So I'm just going to put a literal value of 1 in the plan for now. And if you wanted to remind yourself why, you could put a comment in, using time, I'll just say here, time equals 1 for now. Okay. And so once we've calculated that, then we're going to want to display some output. So we can go ahead and say we're going to display bacteria growth table. Okay, that's our title. And then we can do display for the table headers. So we're told we want headers or headings day and number of bacteria present, which is long, but that's fine. I don't know why I made it so long, but we'll use it. Number of bacteria present. Awesome. Okay, and then if you wanted to dress it up, whatever, we could do something like the following. Fancy. Something like that. Okay, and then with that, we will display the actual day. So the final thing is to display our findings. We know that it's day 1, so we could do something like, okay, there's a 1, and then eventually over here somewhere, we're going to want to display the final population. So let's not worry too much right now about how we're going to get things right, aligned numerically, etc., in these as columns. We'll do that at the very end, okay? But I'll just indicate that we should do something like that by putting some spaces in here. And that's That's basically the program. Okay, we declare some variables, we show up a program title, we get some input, we do a calculation, we do an output. Okay, that's, again, very similar to all the programs we've basically written to this point, unless you've gotten into some of the looping problems. But there's nothing really new there. Okay, but because it's nothing new and we're hopefully familiar with this, it should be pretty easy. So let's just go through and implement this and make sure that this works. And then we can tackle the problem of, okay, how do we put a loop in it, right? That's the new thing that we're learning. And we don't need to complicate the problem solving of stuff that we are already familiar with the learning of creating loops and implementing loops. We can do that after the fact. So let's go now to Visual Studio. So I've already got a project I've created. I've called it Lesson 03 for loop. You can do the same if you like. Pause the video and make that now. But we're going to go ahead and implement our plan. Again, it's nice to have pretty much line by line in our program here. So I'm going to get rid of the scaffold, although we are going to display quite a few things. So I'll take advantage of that here. And let's just get to it, declaring our variables. So we're going to have an int initial population. We're going to have an int final population. And we're going to have a double growth rate. And now here, instead of declaring the constant e as a double, which you can, there's nothing wrong with that, I'm just going to take advantage of the fact that if we look in the math class, there's a property for e here. If you notice, the value for that, right, is just more precise, but it is the same value that we were given in the problem statement. So in C#, we don't need to declare it as a constant. We can just take advantage of math.e. But if you do use const double, capital E, whatever, as assign this value, and you choose to use that in your program, that is not wrong. That is totally fine. And if you were to do something like that and submit it to me, I would be okay with that. No issues. So let's put in our program title. I'm just going to call it Bacteria Growth Program. Right? Again, we can kind of dress this up a little bit. Nothing too crazy. Oops. And then I'll leave a blank line, and then we can get to the rest of it. So the next thing we want to do is get to prompting. So again, we already have that there. We can enter the initial population. And we get that from the user. So that's an int. We're going to have to parse. And we're going to parse from the, console read line. All right, and we'll do the same thing for the growth rate. We can do a console, dot write. And we can say enter the growth rate, indicate here that we're expecting a %. And the growth rate is going to be a double parse. And again, coming from the console read line. Awesome. So none of that's really new anymore. Everyone hopefully feels pretty comfortable prompting for inputs. Okay, and then we get to our setting of the population. Again, we don't have an exponent operator, so we're going to have to make use of math.pow, but we can use math.e here as well. So let's do that. The final population is going to be set equal to the value of the initial population multiplied by, we need to use math.pow, like I mentioned. The base is going to be the math.e property, okay, or the constant e if that's what you defined, and we're going to raise that to the power of whatever the growth rate is multiplied by 1. Now, there's two things we have to do to make this work. One of them is a conversion issue, and the second is a typing issue, okay? Now, the first thing is this. We've asked for the growth rate as a percentage, and so if the user enters in, 7.5, and some of you have already encountered this in previous problems, the number 7.5 isn't how we represent a percentage, right? It's by 100 or %. So 7.5 as a percentage is really 0.075. So we need to make sure we take that input value and convert it so that we can use it appropriately in our arithmetic expressions. So I'm going to divide this by 100, which is not going to be obvious. Like, well, why am I doing that? And so I may include a comment here that says something like divide growth rate by 100 to convert percentage. Okay, now it's clear why I'm doing the divide by 100 isn't part of the calculation to determine the final population. The divide by 100 is because I need growth rate as, it's a percentage. I need to represent it as such. Awesome. Now, the second problem is still with this red squiggly line, which says we can't implicitly convert type double to int, right? That's what it says right here. And if you look closely, the final population we've defined as an int, right? So we're not going to have fractions of bacteria in the population. But this expression, math.pow, for example, returns a double. And whenever you have a double in an arithmetic expression, the result is going to be double. Okay, and so what the compiler here is telling us, it won't even let us run this program, is, hey, look, you're trying to put a fractional precise value into a variable that doesn't support fractional precision. And so that's not to say that we can't do it. It's just implicitly not going to do it, right? If we want to knowingly throw away the decimal portion of a value, we have to explicitly tell the compiler we're okay with that. So because these types are compatible, they're both numbers, but one is just more precise than the other, we need to explicitly tell the compiler, I'm okay with that. Let's typecast this, okay? And so one of the ways we can typecast between these compatible types is to just include the desired type within parentheses. So in this case, if we just wrap int inside parentheses, that will convert or typecast whatever immediately follows it to the right here to that particular type. Now, just doing it in this way isn't going to work, and you'll see right now it gives us this another pop-up that says, oops, hang on. The cast is redundant, okay? And that's because right now the typecast for int is only being applied onto the variable initial population. And initial population is already an int. So saying, hey, make this int an int is redundant, just like the message says. What we want to do, and this is where parentheses come into play, is I want to wrap this entire expression in parentheses and say, no. All this, whatever this returns, we know that it's a double, take that and cast it as an int. We're fine with losing the fractional precision, right? It'll be truncated. We're not rounding. It's just going to go away, and we're going to take the integer value from that and put it in here. Okay, so typecasting can be useful in cases like this where the types are compatible and you are okay with losing the fractional precision. Then you can cast to smaller types. It's not necessary to cast from int to double because that is implicit, right? Whole numbers can be stored within doubles without losing any precision. So we wouldn't have to do this if the tables were turned. If we were trying to take an integer value and put it in a double variable, you don't need to explicitly cast. The compiler will implicitly do that for you. But in cases where you're going to lose precision, then you have to do it. Okay, so that's that. At this point, we've got what I hope is a working program. If we enter known values, so for example, a population of 1,000 and a growth rate of 1%, the value e to the power of 1% is effectively a percent of a percent. So I would expect from the value of 1,000, back of the napkin math, that it would increase by 10. Okay, so you could do that. I would recommend you run through a test plan, as has been shown in previous lectures. I'm not going to put the test plan in here just for time's sake, but again, because I'm not skipping it here, this isn't one of those do as I do, do as I say, not as I do. Make sure you're doing your testing and your planning up front so that you can adequately deal with it. Okay, so let's just run through this and see that we get some kind of desired output. Oh, hang on. I've forgotten one thing here, obviously. So we've calculated final population, this is where planning is useful. We haven't done any of the output, so let's just finish up with the output, and then we can give this thing a test. So let's go to our console, write line, and again, to save time, I'm a bit lazy. We'll just take it from here. I'm not going to copy those funky quotes because they don't come over too good. So we'll have our bacteria growth table. I'll put in a blank line here, and then we can, oops, let's just do this quickly. Let's take our headers. And then we can put in our fancy. It's fine. We'll just have, you're going to see here why you need to be careful when you copy and paste, because you get these quotes which are not good. And then you wonder why your program doesn't work. Make sure if you copy and paste from Windows, or sorry, from Word, that you're going to update those appropriately. Okay, and let's just stretch that out too. And then finally, now we can display our final population on day 1. So the last bit here is going to be console write line. And then here I'm just going to put in a hard-coded value of 1, and I'll use, we'll use string interpolation to put the other variable in. So this is not going to look great. Again, I'll get back to the columnar output later, but for now, we can kind of see what this is going to look like. So final population. All right, so now let's save that. Now we have our output. Now the plan is implemented properly. Let's give it a dry run through and see what happens. So we'll enter a population of 1,000, growth rate of 1%, and sure enough, yay, I get 1,010 as expected. Now, one thing I'd like, again, for the output, we'll come back to this, is to have these values right aligned. Typically, numeric values are right aligned, but we'll come back and we'll talk about how we can do that later on. For now, so far so good. And it's now at this point that we can get to what the lecture is really about. So, I mean, 25 minutes on, we finally get to what we want to know. But again, it's important walking through these solutions to have a good feeling for, hey, these are the steps. I don't really want to skip over those if I don't have to. And I think there's good value in walking through these solutions, at least still at this point, given we're still early in the term. So let's go back to the plan here and now briefly have a look at what is it that we want to repeat. So this is great. We're displaying for day 1, but we wanted to show for days 2, 3, 4, 5, etc. So the first thing we need to do is identify, okay, what are the statements that we want to repeat? And if we look down below here in the program, we definitely want to repeat this. We want to calculate the final population for multiple days, not just day 1. So we want to do this more than once. I don't want to display this more than once. Okay, the table name and the heading row, those should only be displayed once. So I'm not going to repeat them, but I am going to repeat the output for each day and the final population. That is something I want to repeat. So the way this is created at the moment, we can't group these and just repeat them, because then we're going to get this table heading and title over and over and over. So let's just take these out. Let's move those up here so that we're going to first display the headings for the table, and then we can repeatedly calculate and display our output. Okay, so we're going to do a little bit of shifting around. And so now the question is, all right, great, we've identified the statements we want to repeat. How are we going to do that? And if we go back to the problem statement, we know that we're going to be doing this 10 times, okay, days 1 through 10. Now this is important. So the previous videos we've worked through and problems, we've had to repeat statements, but they would be for some arbitrarily or unknown number of times, right? Or arbitrarily determined number of times until the user says no, or maybe based on, some other type of input that we can never know for certain exactly how many times we're gonna create or repeat statements. And so that's a sentinel controlled loop. But in this example, because we can discretely identify the number of iterations we're going to apply here, or it's known, we can know how many times, that indicates that we can implement a counter-controlled loop. Okay, so that's the first kind of thing that I want you to start looking for in problem statements that, maybe have repetition is there a way to know precisely how many times you're going to need to do the repetition? And if there is, then a counter control loop is probably the way to go. And now when it comes to implementing a counter control loop, you have to remember there are really three parts that we have to be aware of. Okay, we need some kind of a count that is going to be used to exactly the way it sounds, count the number of iterations. Okay, so we need that. We need number two to then check that counter to determine whether or not we've reached the desired number of iterations or that we've repeated the statements the correct number of times. And then the third thing is we're going to need to modify the counter so that every time we do something, we keep track of that so we don't repeat it an unnecessary number of times. So those three pieces are things that you're going to want to account for. Okay, and if you go back to the lesson notes and you look at the flow chart and the lesson discussion there, I talk about them in some more detail. So in this example, looking at the problem statement and the formula that we have, the time, this is the variable that is going to change. So every time that we repeat this calculation, the initial population stays the same, the growth rate stays the same, but the time, the day that we're looking at, this is what changes. And so I know I want to do this for days 1 through 10. And so that tells me that the day that we're on becomes a natural counter for the loop. Okay, hopefully everyone can follow my logic there. So what we need to do is we need to, and I'm going to separate this for now just so that we can see this is the new piece. We're going to need to declare a counter here. And if you declared it as named count, that's fine. But I'm going to declare it as day, and I'm going to declare it as an integer because we count in discrete steps, and I'm going to initialize it to 1. The first day that I care about is day 1. Okay, so that's the first part out of the way. We've declared the counter that we can use for our loop. The second thing then is to use that variable, that counter, in a condition to determine whether or not we should repeat the set of statements. So I'm no longer going to be using time equals 1. I'm going to be using our variable for day. And same thing here. I'm not going to be outputting, whatever, 1. I want to output the variable day. Okay, something like that. Or let's just, there we go. So that's an update. And if you wanted to make that update and then go back to your program and test it, see that it's still going to work, you can. I'm just going to say for now it will. If we put 1 in for day and we put day here and day here, we're going to get the exact same output. So that's fine. So the second thing we need to do now is use day in the conditional check. So we can set this up as a precondition loop. And mind you, you can implement a counter control loop using either post or precondition, right? So you could use do while or while. I'm going to choose while because it maps nicely onto how the for loop works. For loop is effectively a precondition loop. But if you wanted to try this with a do while structure, you could. So let's just set this up. The condition to determine whether or not we should perform the loop, the code statements, is, again, we want to go values 1 through 10. So if day starts at 1, I want to repeat these statements while the day is less than or equal to 10, right? If it is day equals 10, then I want to calculate the final population for day 10. If the day is day equals 11, well, I don't. So if this were 11, 11 is not less than or equal to 10, so that would fail, okay? And so, again, the importance of choosing your condition can't be overstated. If you set this up improperly, or you fail to do the third part of the counter control loop, which is to modify the counter in the correct way, then you could end up with what's called an an infinite or never-ending loop where the loop condition never becomes false, and you just get stuck in this loop and it executes until eventually your computer crashes or runs out of memory or something bad happens. You can fry an egg on it because the processor is just working so hard. Okay, so determining the condition is one thing, setting it up properly. Now, if day starts at 1 and we're going to continue to loop while it is less than or equal to 10, what that means for the third part is the way in which we modify the counter has to be such that we're modifying it towards the condition eventually being false, right? So if we started at day equals 1 and every time we executed the loop, we subtracted 1 and we moved away from the value of 10, that would put us into that never-ending loop condition. So we need to make sure that every time we iterate, the day variable, since that's what's used in our condition, is moving closer and closer and closer to that value of 10 and then eventually 11 to get out of the loop. So what we want to do here is set the day equal to the day plus 1. I want to go from day 1 to 1 plus 1, 2. And then we will loop around. 2 is less than or equal to 10. We do the thing. And then we say, okay, 2 plus 1 is 3. And then we loop around, et cetera, et cetera. So 3, 4, 5, 6, et cetera. Eventually we get to 11, which is false, and then we get out. So just make sure you double check that those conditions and the modifications are working in your favor. And that's it, okay? When it comes to implementing a counter control loop, those are the 3 parts. We need a counter, we need to use the counter in a conditional check, and we need to modify the counter within the loop body so that we don't end up with a never-ending loop, okay? So we'll implement it this way first to make sure that it works, and then I'll show you how to convert it to a for loop. I'll introduce a couple of options for how you could do this modification a little bit differently, and then we'll finish up with the columnar output, okay? But that effectively, as far as the solution goes, is all we need to do. We've got all the right pieces. Now it's just a matter of kind of taste and format. So let's go back to Visual Studio and let's implement these changes. So we're going to declare int day. I'm going to initialize it to 1. Again, I'm going to just separate it here because, as it turns out, when we convert to using a for loop, we'll no longer need this here. But for now, we'll map this onto the plan the way that we've made it. So that's fine. We've got to move some things around here. This should only happen once. So let's move our table output away from the repeated statements. We don't, that's fine. So there's a repeated statements here. We're going to do final population calculation. We don't need 1 here anymore. This is going to be for the current day. We don't need 1 here. That's going to be for the current day as well. So those are the simple modifications up front, and now we can put in the looping conditions. So let's take these statements and tab them in because we're going to indent inside of our while code block. Keyword while, the condition is day is less than or equal to 10. Okay, while that's true, we want to execute these code statements. And then the third and final piece is to make sure that we increment the day, in this example, by 1. Okay, so those are the 3 pieces, right? So part 1, this here is part 2, and this here would be part 3. Okay, and we'll get rid of those comments later, but for now, just so we can visually see them. And this is something that the for loop is going to help with. So let's save that and see what happens when we implement or run our program now. Okay, I would at least expect to see 10 output, so there we go. Okay, everything looks pretty good. We've got now, instead of 1, 10, right? And we didn't do much, right? We added a counter, a loop statement, and a modification statement. And the nice thing about this now is if we wanted to show how the population growth was affected over 100 days, all we need to do is change our condition here from days less than equal 10 to 100, and we don't have to change anything else. And again, that's where a lot of the power and repetition in programming comes from. Now, the final thing to say here before I go back to the for loop modification is, I mentioned earlier, some of you might have found another constant to identify, and that would be this, like the days to show or days for growth. And so if you wanted to, I would recommend implement this as a constant. Probably makes more sense. So we could do something like const int days for growth. Okay, and then we would use this variable here in place of the 10. Or at a minimum, I would say if you didn't declare a constant for this, at least put a comment that identifies what the 10 is for. So you would put a comment here that says something like, you know, looping for less than 10 days or equal to 10 days or something like that. But a constant is probably better. It reads better. We're not left asking questions about like, well, why 10? Like, what does that represent? Oh, well, the day is less than or equal than days for growth, do the following. It's almost like our code is what is known as self-commenting or self-documenting. I know what that means. I can read it without even looking anywhere else. And if we wanted, again, to change it from 10 to some other value, all we need to do is make the update here. And all of a sudden, we can see what the table is for 100 days versus 10 days. Very easy to work with. Okay, so that's fine. Everything is looking pretty good. Let's move now to the piece which is what the lecture is really about, and that is implementing this as a for loop. Okay, so we can see that we've got our 3 parts, but they're all in disparate locations. They're all over the code. If there were more statements in this program and in this loop body, I wouldn't easily be able to see where the initialization statement is, or where the condition is, or where the modification is. And what the for loop does is it lets us bring these 3 pieces together in one place. Okay, and the implementation is actually pretty straightforward, and it operates exactly the same way we have these statements laid out now. And that is to say, the initialization happens only once, the condition is checked as a precondition, then the loop body is executed, and then the modification happens. Okay, so here we go. From a while loop to a for loop. We change the keyword while to for. And now within the parentheses, this is where we're going to collect those 3 parts. So the first part is going to be our declaration and initialization. And it's important to note, you don't have to declare in the for loop. You could declare here and just initialize it here or whatever. But oftentimes we declare and initialize. So that disappears, and we just drop it right inside the for loop. So here's the first part, ending with a semicolon. So for, we declare day and initialize to 1. Okay, then we have our condition. While day is less than or equal to days for growth, it's going to execute the statements here, and we indicate the end of the condition with a semicolon. And then finally is the modification piece, sans the semicolon. We take that and we drop that in the 3rd part. Okay, and that's it. Now we've just modified our solution from using a while loop to using a for loop. Okay, hopefully that was clear, and you can rewind this or whatever and review it again. But there's this will behave in exactly the same way as the while loop implementation we had. The difference is we were able to collect those 3 parts into one place, so I can at a glance quickly here know, okay, we start at 1. While 1 is less than or equal to days of growth, or days less than that, we're going to increment it by 1. And then we run through the output statements here. So again, making that change, if you were to run this with the same inputs, I would expect to see the exact same outputs. No change, but we've implemented this now with a for loop. Okay, and that's it. So if that helps, I would recommend while you're learning this, and if you find for loops challenging, don't shy away from them. Okay, so if you like, implement first a solution with a while loop, but then convert it to a for loop where it's appropriate, and practice up, because when we move on in the course and we start processing arrays and lists, even strings, for loops become quite indispensable. They're going to be efficient, easy to use, and we're going to use them a lot. So don't shy away from them. If anything, challenge yourself to master them, so that when it comes time to do the iteration over those collection type data types, that you're ready for it, and the for loop isn't the sticking point. Okay, two final things in this video before I let you go. And the first is other options you can use for modification or incrementation. Okay, so in C#, there is an increment operator. Some of you may be familiar with it. It is the plus plus operator. So as an alternative to being explicit here with day is assigned day plus 1, if you know you're incrementing by 1, you could do something like the following. Okay, so day plus plus effectively does kind of what we just had there. It will increment this day variable by 1. Okay, this is a unary operator. You can put the plus plus, on the end. You can put it in the beginning, although typically it's at the end. It's important to know that where you place it, depending on how you're using it, can have different results, which I'm not getting into. But for that reason, I'm not a huge fan of it, at least not for people that are learning. But it works. So if you use plus plus, maybe you've done some programming before, I'm totally fine with it. The other option is to use the plus assignment or even minus assignment operators. And what this operator does is it is a shorthand for what we just had there. Okay, and the way you read it is take this day value plus 1. So if it was 1, it'd be 1 plus 1, which is 2, and then assign it back here. Okay, so this is the equivalent of that. Okay, this is very explicit. This is the kind of shorthand version of the explicit version. And I'm kind of partial to this option here. It's clear without, taking up a bunch of space. So I'm totally fine with any one of those three options should you choose to use them. But in the beginning here, at least while we're starting to learn about these types of loops, I'm going to use the very explicit option so that people are okay with what's going on and it's easy to read. Okay, the final thing we need to do, and then we're done here, is deal with the columnar output. So at present, we're not really having right-aligned values and everything looks kind of messy. And if you review the formatting console output document that's available to you in the class, how you can go about formatting your output, not only for numeric formats, but also for columns, whether you're left aligning or right aligning values, is all presented in that document. So I encourage you to review that document, but I'll go through the quick implementation of it here. The simplest way to get everything to line up is to, everywhere we have output, utilize the same formatting. So what I mean by that is, if my day column is going to take up 3 spaces or 3 positions, I want to format it so that no matter what I put out in this position, I know it's going to take up three positions. And we can do that with string interpolation. So I'm going to first of all convert these string literals into interpolated string literals by putting $signs on front. And then I'm going to wrap my output variables, or values in this case, so literal string day, and then we can specify the number of spaces that, or number of positions that output should take up by using a comma and then specifying the number here. Okay, if this were a number that you wanted to format, you could then follow up with the :C or whatever for the numeric output. But for lining things up, this is what's going to work. So this says take this value, the literal string day, and make sure it appears in 3 spaces. And if we were to count this out, we'll see I think we have 26 characters. We can do the same thing for these values. So we'll leave a single space in between. We can use the literal string number of bacteria present, and I'm going to line that up in a column of 26 characters. And then we just apply that everywhere that we have output. So what that means is I would do the exact same thing here. I'm going to say, okay, I want these equal signs to take up 3 spaces, a single space. I'm then going to have here this output do the same. This is 26 spaces. Okay, fantastic. And then finally, the only other place we're doing output on our table is here. And we do the exact same thing. We don't have to guess by spacing things around. We can say, no, output the day variable. Make sure it, in this case, is right aligned within 3 characters. 1 single space, and then the same thing with final population. Output that. Make sure, again, it is right aligned with 26 characters. And so as long as these are all in agreement, so we have this value for 3, this value for 3, this value for 3, these should all be aligned. And here we have this value for 26, this value for 26, and this value for 26. These should all be aligned. Okay, and that's how you can go about doing your alignment. And if we run this, and I'll just use some larger numbers here. So let's say we do, and we have a larger growth rate, 67%. Now you can see that even though, you know, the digits change from 1 to 2 or right, whatever, 5, etc., 4 on, everything is still displayed in either the 3 character spaces here or within the 26 here, and they are right aligned, nice and neat, makes reading of tables super easy. Now, if you wanted things to be left aligned, let's say you had textual output that's typically left aligned, then you would just precede these number of spaces that you want, the desired space count, by with a minus or a negative sign, and then that would do left alignment. Okay, but all that is written up in the formatting output for the console document that you can find on Moodle. And so that's it. Again, I don't have a test plan to go about checking my actual to expected output values, but hopefully you would have done that if this were a problem that you would have tackled on your own. But we're already hitting the 50-minute mark, and so I don't want to take any more of your time. Hopefully you found this video useful. As always, if you have questions, let your instructor know. But that's it for now. We'll see you next time.